Okay, Assalamu alaikum warahmatullah. Good evening, everyone. So, on behalf of the Sudanese Doctor Association in Qatar, we would like to welcome Prof. Suhail. Um, just a note: this lecture comes as a lecture towards Sudan's commitment towards the Research and Publication Office from Qatar University when they did their competition, Siraj al Sudan, for the young researchers who put out their proposals. And this was one of our commitments towards the competition as a diamond sponsor. So without further delay, I'll present Prof. Suhail. And before that, I want to give a huge thanks to Dr. Muhammad Hamza, who is an assistant professor of physiology at the Qatar University, for putting the effort on contacting Prof. Suhail and Dr. Habib to make those sessions into action. So we have Prof. Suhail Doi, who is a professor of population medicine and clinical epidemiology at the Qatar University College of Medicine, where he heads the Department of Population Medicine. He's a clinical endocrinologist by training, and he is a fellow of the Royal College of Physicians of Edinburgh, Scotland. He transitioned from clinical practice in endocrinology to clinical epidemiology once he became a consultant. After obtaining his master's and PhD in clinical epidemiology from Australia, he has established himself as a leader in this area, proceeding to write two books on clinical epidemiology and many methodological papers dealing with methods of interest to researchers. He has a keen interest in the methods used in the evidence synthesis, and key examples are methods for aggregate data meta-analysis, like the QE model, those response meta-analysis, REMR method, the network meta-analysis, diagnostic meta-analysis, and the dot plot for bias assessment. And we can clearly spot that it's after his name, which put him as a pioneer in the field. Many of his methods are available as data modules for researchers. In addition to methods development, he has a keen interest in outcomes research in the area of endocrinology, metabolism, obesity, and diabetes, and he has led important clinical studies in this broad area, including gestational diabetes, polycystic ovarian syndrome, thyroid cancer, and related areas. He has over 250 publications listed on PubMed, and he's highly cited and listed among the top 2% scientists in his field. So, as Dr. Hamza has mentioned, we are really privileged to have Prof. Suhail with us today, and we really advise everyone to make the maximum use of his expertise and his knowledge. Prof. Suhail, the floor is yours.
All right, thank you, Dr. Khalid. I will now proceed. Okay, thank you for that kind introduction. So let's move on with today's topic, which is p-values and confidence intervals and hypothesis tests. I mean, they're all related to each other. So the way I will proceed is by just showing you this normal distribution on the screen. What is this normal distribution? This normal distribution is a probability distribution. Now, there are two types of probability distributions. There are sampling probability distributions, and there are just probability distributions of individual measurements. Now, when we look at individual probability distributions, they can take any shape. So you can have a uniform distribution, you can have a binomial distribution, you can have a de la Porte distribution, etc., etc. And those distributions depends on what actually is being measured. So for example, if I flip a coin, the probability of a heads, for example, would follow a binomial distribution and so on. So if we were looking at individual flips, that's the sort of distribution we are looking at. Sampling distributions, on the other hand, are distributions of sample statistics. So, in other words, if I have a population and I draw a sample from a population of a certain size repeatedly, so let's say a population of Qatar, and I draw a sample of 100 people repeatedly, from which I take a mean, for example, and if I have thousands and thousands of means, and then I look at the distribution of the mean. That's a sampling distribution. Now, given the central limit theorem, sampling distributions only have one shape. and that's the normal distribution. Make sense? So a sampling distribution is a distribution of sample statistics of a certain sample size taken from a certain population in a certain way. That's what we call a sampling distribution. It's usually always normally distributed. And what you see on the screen in front of you is a sampling distribution, right? Now, this sampling distribution has been given many names by many people, but the most famous name given to it was by Ronald Fisher in 1925 when he came up with his book, where he called this sampling distribution a null hypothesis. And he had a reason for calling it that. Over the years, now 100 years since 1925, we are in 2025, and over these 100 years, people have given different names to this sampling distribution of sample statistics, which are generated from repeated sampling of the same size. So, although he called it a null hypothesis, other people called it the model hypothesis, other people called it the tested hypothesis, and so on and so forth. And all these names were given to the sampling distribution in the context of a p value and hypothesis testing. So
So,
outside the context, yes,
sorry
anybody
for
has?
interruption, Prof. Uh,
Yes, sure.
to me, it's shown only the first slide. I'm not sure if it's the same for everyone or it's only me.
Yes, I'm still on the first slide because it's the
Okay.
most important
Just
one.
the intro. No, no, just the introduction slide. Not the one is what is the p-value.
Oh,
I'm just seeing
Yes,
the
I
very
think.
first slide.
okay.
Thank you, Dr. Khalid. I think so. Yeah.
Can you see it now?
Yes, yeah,
Yeah,
perfect.
yeah, yeah. Yes,
Yeah,
it's
yeah.
Yeah,
clear. Thank
I
you.
have this problem sometimes when I play it, it doesn't move. So what I have to do is I have to play it first and then share it. Give me a second, I'll do that.
No problem.
I'll I'll play it and share it. That's the reason why this is not working. So I have to stop the share and then I'll play it on my side and then share it. So then it will move. Okay, so now I'll
Please, Professor Suhail, please can you
yeah.
repeat it again with your slideshow?
Yes. Now can you see it moving? I'll just try moving it. Can
Okay,
you
yeah, yeah. So clear, yeah.
yeah, can you see it moving now? Is it moving?
Yes, yes.
Yes, yes, it's moving.
Okay. So this was a slide I was on, the first slide. So maybe I should recap and say this slide shows you a sampling distribution, which is different from a sampling probability distribution, which is different from a simple probability distribution, right? And so everything I was talking about applied only to this slide. Okay. So now that you understand that this is a sampling distribution, it has different names. Now, the reason Ronald Fisher called this a null hypothesis was that a sample statistic he was interested in was the difference between a hypothetical population mean and your sample statistic of interest. So if you are going to do that, if you take such a difference, now keep in mind you're actually looking at a difference between a hypothetical population parameter and a sample statistic. This difference is called a test statistic. So, in other words, you're simply just transforming your sample statistic. Let's say our sample statistic is the sample mean. We're simply transforming it by taking a difference from the mean that's of interest to us and dividing it by the standard error. So once we do that, we standardize the value of this sample statistic of interest to us. Let's say it's a sample mean, and it becomes a test statistic on a standardized scale. And this was done very early. My guess is this was done even before Ronald Fisher in 1925, but he was the one who sort of formalized this. And the advantage of doing this is that this sampling distribution that you see on the screen becomes a standard standardized distribution, which means whatever you are measuring in your study, once you standardize it, then the set of possible results, which as you can see, if you look at my arrow on the x-axis, would be standardized in such a way that 0 would represent a sample statistic that is equal to the population parameter. It's a hypothetical population parameter, right? But 0 would represent that. And this would be, it would represent the mean. And that's why he called it the null hypothesis. I don't know if people are, if you are following what I'm trying to say here, but that's basically how this whole idea was brought up. In other words, you have a probability distribution. This probability distribution represents repeated sampling from a hypothetical population. And because you're creating a test statistic, which is difference between the sample mean and some hypothetical parameter value, you now get a distribution of test statistics, and that distribution of test statistics will be centered on 0. And that set of possible results, depending on the sample size, is what we call a z-score or a t-score. So now what you have on this x-axis, instead of the possible means from repeated samples, you have t-scores or z-scores. And let's keep it simple. So we'll just say z-scores, and we'll assume sample size are large. You have z-scores on the x-axis and the probability of the z-score on the y-axis giving you this curve. Everybody's clear so far? If there are any questions, this will be the right time to ask. Anybody has any thoughts on this? Would like to ask any questions?
I have a question, Professor.
Yeah.
If in my sample I have some odds, large numbers or very small numbers,
Yeah.
does they include in this in this
Yeah.
in this curve, or
Yes. So
it
for
might be
example,
outside?
yeah, so let's take, yeah, a good question. Let's say you have an odds ratio from a study. Let's say a study of 100 people divided into two groups, for example, and then you get an odds ratio, correct? That log of the odds ratio has a standard error. Keep in mind, the odds ratio doesn't have a standard error unless you log it, right? So the log of the odds ratio has a standard error. You can create a z-score, and you can create the same sampling distribution for that z-score. Now, keep in mind, I'm saying that you are creating this curve by repeated sampling from a hypothetical population, correct? But if the population is hypothetical, how do you do repeated sampling from an imaginary population? That you get the idea. If you had a real population, and you knew what its true value was, and then you did repeated sampling from the real population, you can get thousands of samples and plot this curve. The idea that Ronald Fisher floated was that we know the equation of this curve. We know the probability density function, which means that if we know what the population parameter is, without repeated sampling from the population, we can create this sampling probability distribution without repeated sampling. In other words, they all follow the same probability density function, which means that all I need is your sample size and your hypothetical population parameter, and this curve can be created that shows the distribution of samples of that size for the value, whatever value it is that you are interested in of the hypothesized population parameter. And so it just shows you the distribution of samples of a statistic you're interested in. It can be any statistic. I said sample mean, right? You gave me odds ratio, fine, anything that is normally distributed. So if it's odds ratio, relative risk, or whatever, you have to convert it to a log to make it normally distributed so it has a standard error, right? And we use the sample standard. So we use the standard error derived from the sample standard deviation as the unknown population standard deviation. Keep in mind, I'm calling it standard deviation because it's a standard error is a standard deviation of sample statistics when you distribute them as we are doing here. So, in summary, what we are looking here is a probability distribution that represents the hypothetical population had we sampled from it repeatedly samples of the same size and plotted the results here after converting them to test statistics. Make sense? Everybody clear? This now I'm not going to move forwards until this is clear to everyone, because this is the most misunderstood concept when it comes to p-values and confidence intervals. So you need to understand what is a sampling probability distribution in order for us to move forward. Everybody is clear on what's that?
It's very clear. But Professor, do you think at any point you can add an example?
Yeah, I'll add an example as we move ahead.
Okay,
But
thank you very much.
this whole concept needs to be clear.
Yes,
Just
it
give me
is correct.
1 second. I think there's some background noise. I'm going to ask them to stop making it. Okay, so now that this is clear, now I'm going to move on to the next concept, which is the p-value comes from this probability distribution. In other words, I know now how to create this sampling probability distribution for samples. So I do a study, right? My study size is 100, so my sample size is 100. I hypothesize an odds ratio of 1 as the population parameter. Let's assume. I get an odds ratio, whatever, 5, 4, 3, whatever I get. I create my test statistic. At the same time, I create this probability distribution. Then I take my sample result. So this is my sample result, this green dot here. I put it on the x-axis wherever it falls on this sampling probability distribution. And the area to the right side, the one in blue, the area to the right side, and if it's a two-tailed, to both the right and left side symmetrically, that area is my p-value. This was the idea brought up by Ronald Fisher in 1925. And he called this whole idea of his, he formalized it and called it significance testing. You got the idea now. So there are two types of testing. There is significance testing in medicine and in other fields as well. And there is hypothesis testing. So there are two different things. Now, hypothesis testing was not set up by Ronald Fisher. Later on, I think in the 1930s, Neyman and Pearson, two different people, they extended significance testing to hypothesis testing. And so I'm going to talk about that as well. But let's understand Ronald Fisher's significance testing. It was about creating a probability distribution, a sampling probability distribution. And he called it a null hypothesis because he always chose no difference as his mean hypothesized population parameter. So for example, for odds ratio, that would be 1, right? And so the log of 1 is 0. So the mean of this distribution would be 0. And then you create this uh, uh, probability distribution based on your PDF. So you can calculate it without doing repeated sampling. Once it is calculated, you then take your sample value, whatever you got, and you plop it wherever it falls on the x-axis of this distribution, which is here, right? And then you take the area. If it's one-tailed, you just take the area to the right. If it's two-tailed, you take a symmetrical. So keep in mind, you have converted it to a z-score. Let's say this z-score is 2. Then you add the area to the right of 2 and also the area to the left of -2 on this side. And that sum of areas, keep in mind, the whole area under this curve is 1, right? So maximum you can have is 1. And the area onto either side, if you sum it up, is your p-value, which varies between 0 and 1. Okay? Now, this p-value, the further it is from the center. So if your value fell in the center here, then on the right hand side you have 50%, which is zero point 0.5. On the left hand side you have 50%, so your p-value would be 1. And as your value falls to the extremes of this distribution, your p-value starts to decrease until it becomes a very negligible value. Keep in mind, this curve is asymptotic, which means it never hits the x-axis, and therefore it can go all the way to infinity. And then he came up with the idea that if your p-value, which is the sum of the two areas in the tails, beyond your study value, if the p-value is less than 0.05, which is 5%, he said that that suggests that your result is statistically significant. I think that was the biggest mistake he made in his lifetime, to call this result statistically significant. Because what he actually meant was statistically unusual. But instead of calling it statistically unusual, he called it statistically significant. Now, significant means many things to many people. For example, we can say Yom Al Arafah is a significant day. That means it's a great day. But Ronald Fisher did not mean significant in terms of something great. He meant significantly different or significantly away from the probability distribution. In other words, given this population parameter of 1, odds ratio of 1, your data and your result is unusual. And therefore, you should consider another probability distribution for, which means another population parameter for your result, and not this one, not this hypothesized one that you just hypothesized. Does that make sense? That's all that significance testing is about. Significance testing is get a p-value, and if the p-value is very low, get a p-value for your study result under an assumed probability distribution, which has an assumed mean, which is the population parameter. And if your p-value is low enough, then under the constraints of this probability
Okay.
distribution. Yes, go ahead. You have a question?
I think it's by mistake, Prof. We can
Okay.
continue. Sorry about
So
that.
under the constraints of this probability distribution, whose mean value is, now keep in mind, all sampling probability distributions are known by their mean values. So this one is a mean value of 1 on an odds ratio scale. So we call this a null hypothesis. So this probability distribution is called a null hypothesis. If you put your sample result on this one and you get p-values that are less than 0.05, then it's highly unlikely that this distribution, or rather this population parameter, or a population whose parameter is the mean of this distribution, was responsible for generating your study data, and some other population is where your study data came from. That's the concept of the p-value and significance testing. Everybody clear on this? That's it. So this just one slide, I haven't gone to the next slide yet. Just one slide captures the essence of what's a p-value, how was it conceptualized, and what does p-value less than 0.05 mean. It doesn't mean you have an important result. It doesn't mean that you have a great result. It doesn't mean that your result is dramatic. It doesn't mean that your result is useful. All it means is the hypothesized mean of this distribution, which was the odds ratio of 1, is not the population parameter that is likely to have generated your study data, and some other population parameter exists from which your study data has emerged. Does that make sense? That's it. This is what a p-value is. And this is something that needs to be very clear to everyone. And so I hope I've clarified that. And this whole idea of coming up with a p-value is called in statistics today significance testing. So when you say I'm going to do a significance test, this is what you mean by significance test. You get a p-value, and nowadays it's automatic. These probability distributions are created by software. As soon as your sample, you did your analysis, whatever you did, your software will create this in the background, compare it against your sample estimate, and give you a p-value and plop it into your results. This is what's going on in the background. Make sense? Okay, so this is all I'm going to say about significance testing and p-values. Now we come to hypothesis testing. Okay? In hypothesis testing, we have a slightly different scenario, right? In hypothesis, so you see, the problem with significance testing is, if I go back to the previous slide, the problem with significance testing is if I increase my sample size, let's say I did a test with a sample size of 100. If I double my sample size, and let's say I got a p-value of 0.5, let's assume. As I keep on increasing sample size and repeating the significance test, I will reach a point where my p-value will drop below 0.05. In other words, two things determine whether you are going to get a statistically significant result or not. And one of them is sample size, which means a statistical significant result is inevitable. Just a matter of increasing your sample size and you will get a significant p-value. Or if you have a large enough effect size, you will get a significant p-value. So in other words, both sample size and effect size will end up giving you. So Neyman and Pearson thought about this and said, this is not good enough. How do we distinguish sample size from effect size? And that's how hypothesis testing was born, because Ronald Fisher did not make this distinction. He only talked about significance test, and then he left the rest to everyone to decide. And so these guys came about, and they brought in the alternate hypothesis, right? So with significance testing, there is no alternate hypothesis. You just have your null hypothesis. With hypothesis testing, we now have a alternate hypothesis and a null hypothesis. Now, this curve that I showed you on the screen here, this curve, this is your alternate hypothesis, okay? The null hypothesis is between these two dashed lines, okay? So just imagine a curve that's between these two dashed lines. That's your null hypothesis. And your null hypothesis has a mean of 0.5. So let's assume your null hypothesis has 50% reduction in relapse. Your alternate hypothesis is that there is actually a 70% reduction in relapse. Okay? This is your alternate hypothesis. So if you have these two hypotheses, now you can decide whether you want to reject or fail to reject the null given the constraints of your alternate hypothesis. That was the idea that Neyman and Pearson brought up in the 1930s. And the reason they got the alternate hypothesis was that, let's say, so the p-value was not important anymore for Neyman and Pearson. So you see, when you go back to Ronald Fisher, the exact p-value was very important. Is it 0.05? Is it 0.01? Is it 0.006? Is it 0.3? The exact p-value was relevant. Here, with Neyman and Pearson and hypothesis testing, they said just decide what your critical value is, what your threshold is. So let's assume we take the same threshold, 0.05, right? If given the alternate hypothesis, you have to specify the alternate hypothesis, and then you have to specify one more thing. And that was, they brought it in. You have to specify type 1 and type 2 errors. This was brought in by Neyman and Pearson. So there are no type 1 and type 2 errors with Ronald Fisher and significance testing. But with hypothesis testing, their type 1 error was the threshold p-value at which you define statistical significance. They called it a type 1 error. and they fixed it at the same value as Ronald Fisher, 0.05. They said, okay, you fix your type 1 error at 0.05, and then you fix your type 2 error at a value that's suitable for you. And in their initial paper, they suggested you fix your type 2 error at 20%, right? And then given a type 2, that type 2 error will fix your sample size, right? And then given the type 2 error that you accept, if your p-value crosses the type 1 error threshold, which is 0.05, you reject the null hypothesis. If it doesn't, you fail to reject. You cannot accept the null hypothesis, right? You can only reject it or fail to reject it. This was what hypothesis testing was all about.
Sorry,
And if,
Professor.
yes,
According to what can I choose my, according to
sorry.
sample, according
Uh,
to what can I,
yes, so I'm coming to that. So the question
yeah,
now is, how do you decide what is an appropriate sample size, correct? That was the whole idea of hypothesis testing. Well, they said now keep in mind your type 1 error, if you assume a hypothetical null distribution here, your type 1 error is just the zero point zero 0.05 point on that distribution, okay? Which is this dashed line. So you see the dashed line, these two dashed lines are at the 0.05 point on the null distribution, okay? Where that 0.05 line cuts the alternate distribution, on the left side is your type 2 error, and on the right side is the power of your hypothesis testing. And in this example, the power is 42.1% at a sample size of 20. So you see the sample size 20 here? At a sample size of 20, my 0.05 threshold on the null hypothesis cuts the alternate hypothesis at 0.72, leaving an area of 42% on the right side, giving me, so 1 minus type 2 error is your power, giving me a power of 42%. This is not good enough. So according to Neyman and Pearson, at least we should have 80% power to have a valid rejection of the null hypothesis at your type 1 error threshold of 0.05 or whatever it is that you chose. Does that make sense? So this was the whole idea. So now we can see 20 is not suitable. So I can go to a sample size of 50. This is the same scenario here, except that now these probability distributions have shrunk, and the reason they have shrunk is your sample size is increased, right? Which means that the power has increased to 82%. Why? Because the zero point zero 0.05 line on your null hypothesis now cuts this alternate hypothesis at a point which gives us a power of 82%. And if I want to increase the power further to 90%, I can increase sample size even further, right? If I increase the sample size to 62, again, the two distributions shrink. Keep in mind, probability distributions, whether they are the null distribution or the alternate distribution, their height and width are going to be exactly the same for the same sample size, except for their mean value. So you can see the null distribution, you can imagine it to be exactly the same shape, height and width, but in between these two dash lines, right? And your alternate distribution is this one that's shown here. And you can see the only difference between the two of them is the mean. The mean here will be the null value, which is zero point 0.5, and the mean, this null value you chose, right? And the mean here, 0.7, is your alternate, which again you chose. So zero point 0.5 and zero point 0.7, these mean values of zero point 0.5 here and zero point 0.7 here were chosen by you. And then you create the probability distributions, and then you calculate where the 0.05 threshold cuts the alternate, and then you get your power on the right side and your type 2 error, which is this white area on the left side. You get the idea? So this was how hypothesis tests were formalized. In a hypothesis test, the threshold needs to be defined for the p-value, but the exact p-value became irrelevant, right? You decide on a threshold. Let's say your threshold is 0.05. That became your type 1 error. And then you decide a threshold for type 2 error. Let's say it's zero point 0.1, as in this case. And then you draw your curves. Now you have two curves, not one. And then you take your sample, right, and you plop it on the x-axis. If your sample crosses 0.62, you reject the null hypothesis. If your sample doesn't cross 0.62, your sample value, you do not reject or fail to reject the null hypothesis. This was the hypothesis testing. This was the 1930s. And then over the years, what happened? Textbooks came up in statistics, and they gradually merged significance and hypothesis testing together, and they came up with a new term. It was called NHST, null hypothesis significance testing. And so from the 1940s, 1950s, null hypothesis significance testing became just one thing. And it was combined and presented as such in many textbooks, which created the dilemma that we face today. Nobody understands what is null hypothesis significance testing, what does it mean? But I hope this clarifies it. So this is basically the distinction between a hypothesis testing and a significance testing. And I've given you an example, as one of your colleagues suggested I should give you, that clarifies everything. Now, in this same example, if I remove the null hypothesis, let us say I got a sample, my sample mean relapse, reduction in relapse was, let's assume, was 70%. Let's assume that's my sample value. If I go back to my first scenario with sample size of 20, 0.7 would not allow me to reject the null hypothesis, correct? If we're doing hypothesis testing, and my p-value would be less than 0.0, will be more than 0.05. 0.05 is at 0.72, right? So if my value was zero point 0.7, I would neither have statistical significance, nor would I reject the null hypothesis. If I went to sample size of 50, now zero point 0.7 is on the right side of this dashed line. Now I will have a smaller p-value than 0.05, so I'll have statistical significance. I would also be rejecting the null hypothesis. Now, keep in mind, the rejection of null hypothesis requires the alternate distribution. The p-value does not require it. So I can have a p-value with this sample size, I can have a p-value with this sample size, I can have a p-value with this sample size. But once I fix my power, I can only reject the null hypothesis with this sample size if I chose a power of 90, or reject it with this sample size if I chose a power of 80. If I had a power of 42, I have no credibility in rejecting the null hypothesis. I can just report significance testing. I would no longer be able to talk about rejection or not of the null hypothesis. Does that make sense? This, in a nutshell, is what we mean by significance testing, by p-values, and by hypothesis testing. Does this make sense to everybody? Because this is the most misunderstood concept. Most textbooks deal with it completely incorrectly, and therefore no guidance has been given to clinicians, and people have been misled over the years about what's a p-value, what's a significance test, and what's a hypothesis test. So that's all I'm going to say about p-values and hypothesis and significance tests. Is there anybody who would like to ask a question? Okay, since everybody is crystal clear on this, hopefully you will not make the mistake in the future of saying that a significant result is a good result, an important result, a great result. No, it has nothing of that implication. A significant result is unusual given the probability distribution that you hypothesized. That's it. In other words, Your data doesn't come from that probability distribution. It comes or doesn't come from the population parameter defined in that probability distribution. Some other population parameter is the population. Some other population with some other population parameter is the population that generated your study data, not the one that you hypothesized. That's the only implication of either significance testing or hypothesis testing when you reject the null hypothesis. Okay, that's it about hypothesis tests. If you are still unclear, this has been recorded, so you can go back and listen to the recording and a few times, and that might clarify things. Now let's come to the next thing, confidence intervals. Again, this was not Ronald Fisher. This was Neyman and Pearson in the 1930s. I think 1937, they decided we should have something called a confidence interval. Again, calling this a confidence interval, just like Ronald Fisher made the mistake of calling it a significance test. He should have called it a divergence test, or he should have called it an unusuality test. But he decided to call it a significance test. These guys, they should have called this an uncertainty interval. Instead, they called it a confidence interval. There's nothing, we are not confident about anything here. But just to highlight it to you, let's say I did a study of the same sample size. Let's say I did it 20 times, right? And let's say Allah had told me what the true population value was, this black line here. Now I created this interval from 20 different studies. You can see this is a 95% confidence interval. All that it indicates is if I did the study multiple times, 95% of the intervals would include the population parameter and 5% would not. So this is 1 out of 20, that's 5%. So one of them doesn't include the population parameter, the rest of them do. So when you talk about a 95% confidence interval, it is about when you do a hypothetical repetition of your study thousands of times, you will get thousands of intervals, of which 95% of those thousands of intervals will capture the population parameter, and 5%, which is 1 minus 0.95, 5% of such hypothetical intervals will not contain the population parameter. This was Neyman and Pearson's definition, and they call this a confidence interval because in the future, if the study was to be replicated, 95% of them would indeed capture the population parameter. There's one big problem with this. We only do one study. We have no need, we never do thousands of studies and make inferences about thousands of intervals. So this whole idea was totally useless. What we want to know is the single interval that we create, what is its interpretation? We want to know what is the long run interpretation of thousands of intervals, because that doesn't help us. So let us say my interval was this first interval here. After the interval is created, there's 100% probability of it containing the population parameter. If my interval was this red one, after it was created, there's 0% probability of it containing the population parameter. And the problem is, I don't know which is my interval. Is my interval the 0% probability interval, which is this red one, or is mine the 100% probability interval, which is all of these? Because the probability after I create my interval is different from the probability before I create the interval. So Neyman and Pearson's probability for the confidence interval was the probability before the interval is created. That's your future probability. Only Allah knows what it is. What we have after you create the interval from your study is it's either a 0% interval or it's a 100% interval, and that's not good enough, right? So we need some other interpretation of the confidence interval. So I'm going to give you another interpretation that will clarify what this interval that you created, what exactly is it? Okay. Now have a look here on the screen. Can you see the probability distribution that's moving? Can you all see a moving probability distribution?
Yes.
Yeah,
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 yes, you
yes.
can see it.
Okay, so this moving probability distribution is what we call the sampling distribution I talked to you about on my first slide. Okay, so this interval is indicated by the two red arrows. So this is the lower limit of the interval here. This is the upper limit of the interval. This is my confidence interval. I call it uncertainty interval, but you can call it confidence interval, it doesn't matter. So this confidence interval is indicated here. Now, this interval is actually an interval of test hypothesis. You see this test hypothesis that is moving? It's interval of that. In other words, in between the lower and upper margin of your interval lies thou- uh, literally thousands of test hypotheses, and each test hypothesis, as I told you, for a fixed sample size has the same shape and size, only the mean is different. So in other words, that if you're here, the your mean sample from your sample was zero point 0.7, let's assume this interval is zero point 0.3 to 1.1 or zero point 0.4 to 1 or whatever. Let's just assume that you had some values, or let's make it easier, zero point 0.6 to zero point 0.8. Let's assume this was your interval, right? 0.6 to zero point 0.8. Then each of the values, 0.6, 6.1, 6.2, 6.3, all the way to zero point 0.8 is is the mean of a different test hypothesis, or what Ronald Fisher called null hypothesis. In other words, this interval is an interval of test hypothesis. And if we have a 95% interval, it means that under this, the test hypothesis in the interval, so here your interval is zero point 0.6 to zero point 0.8, all test hypotheses ranging from zero point 0.6 to zero point 0.8, if you were to take your study result and plot them on the x-axis of the test hypothesis, the p-value you would get would be less than 0.05. That's the meaning of a 95% confidence interval. It means that on all of these test hypotheses, your data would fall between the two dashed lines. So just make an assumption that on each of these distributions, there are two dashed lines representing the cutoff of 0.05. Where did we get 0.05 from? This is a 95% confidence interval. So 1 minus 0.95 is 0.05. So in each of these distributions, your sample will fall between these two dashed lines. You got it? Now, if the distribution is within your interval, then your data falls between these two dashed lines on the distribution. If your distribution is outside the interval, then your sample, now keep in mind this black dot is your sample. Your sample value is always the center of your interval. And you can see when this distribution goes outside these two red arrows, your black dot is outside the two dashed lines. When your tested hypothesis is inside your interval, this black dot is between these two dashed lines. You get the idea? So now we can make a definition of the confidence interval. It's an interval of test hypothesis under which your data, which means the mean value you got from your study, which is zero point 0.7, your data will not be unusual. You got it? It's an interval of test hypothesis under which your data would not be unusual. Any test hypothesis outside your interval, your data would now become unusual for that test hypothesis. And how do we define unusual? We define it based on 1 minus the value for the confidence interval. So if your confidence interval is a 95% confidence interval, you define unusuality as 1 minus 0.95, which is 0.05. So a p-value of 0.05 would happen only if you tested your data against a hypothesis that's outside your interval. All hypotheses inside your interval would not give you a p-value of less than 0.05. The same applies to whether you have a p-value, if you have a 90% confidence interval, then your threshold is 10%. If you have 50% confidence interval, your threshold is for unusual is 1 minus zero point 0.5, which is zero point 0.5, and so on and so forth. So this is now the interpretation of the confidence interval. It's an interval of test hypothesis under which your data would not be unusual given the threshold defined by your confidence interval. This is a 95% confidence interval. So the threshold is 1 minus 0.95, which is 0.05. Everybody clear with this definition? This is the only valid definition of a confidence interval. Any other definition that are given to you in the textbooks are not correct. And there's a lot of misinformation in the textbooks that we see today about what a confidence interval really is. And there have been many debates in the literature. People have said, let's not call it a confidence interval, let's call it a compatibility interval, meaning that these are the test hypotheses compatible with your data. This was Sander Greenland who suggested that. Andrew Gellman said, no, I don't think this is a compatibility interval, this is an uncertainty interval. It gives you the uncertainty in test hypothesis that could have generated your study data. In other words, it gives you a range of population parameters under which your data would not be unusual, given the threshold you set for the confidence interval. So these are all different definitions, but so long as you understand it, what it means, you can call it whatever you want. Make sense? So I'll give you an example here. Let's say you gave an intervention for weight loss, and your study was measuring weight loss difference. Okay, so you have two interventions. What's the difference in weight loss between the two interventions? And your null hypothesis is that there's no difference. So the difference is zero. And then you create your null hypothesis, which is your probability distribution around it. And then you did a study and you found 3 kilos weight loss. So you plot on the x-axis, you plotted your result, and you find that your z-score, right, is point, your z-score is 3, okay? And then you got your p-value, which is, so you can see the p-value is here, and you've got a p-value at the location, which is 0.0027, right? So this is your p-value, this is your z-score, this is your percentile location, you can forget about that, and this is your difference in weight loss. Now keep in mind, because we chose a sample size that gave you a standard error of 1, the actual difference in weight loss and your z-scores are exactly the same. But that's just coincidental, right? And that comes with choosing a sample size that gives you a standard error of 1. Okay, so now that we have got that clear, what is this? This is a significance test. I can also create an interval. I can also do a hypothesis test if I had an alternate hypothesis. They're all related to each other, not much different from each other. This is an example of multiple intervals. So you can see that at each, let's take the 95%. So this is 95% interval here. So it starts at this first central dashed line and ends at the next. So you can see for the same example of weight loss difference, you got 3 kg as your mean, right? And you can see the mean is 3 kg here. This is your mean of 3 kg. Your interval is 1 to 5 kilos, all right? So 1 kilo is the lower boundary of your confidence interval. 5 kilos is the upper boundary. And you can see The lower boundary is its own probability distribution. The upper boundary is also its own probability distribution. And you can see that for the upper boundary, okay, this upper boundary is the threshold for this lower distribution, and the lower boundary is the threshold for the upper distribution. And that's basically how the whole thing is conceptualized. And you can have multiple types of intervals. For example, the bottom one is a 99% interval, and then you can have a 50% interval. So as you decrease the confidence interval value, your confidence interval gets more precise but more unreliable, right? And you can see at a 0% confidence interval, which is the one on top, there is just 1 point, which is your mean value. So this is how confidence intervals are conceptualized. And keep in mind, your threshold for a 95% confidence interval is 5 percentile or 5%. For a 80% confidence interval is 20%, and so on and so forth. And so this is basically, and we're talking about two-sided p-values here when we talk about two-sided percentile threshold. So this is how the confidence interval is conceptualized. Now let's put everything into practice. Let's take the confidence interval for 6 hypothetical studies of weight loss difference. And you can see in these 6 studies, we've got different weight loss differences. Here we have 10 kilos weight loss. Here we have 2.5 kilos. Here we have like 15 kilos and so on. So these are all different kilos of weight loss. And we also have different confidence intervals for all of them. So I'm going to ask a question here. How do we interpret it? Now keep in mind the null value is 0, which is this straight line here. And plus or minus 5 kilos is our range of clinical indifference, which is the dashed lines. In other words, if you lose or gain 5 kilos, not really important to you because you can do that without the intervention. And so the question now is, values within these dashed lines are not clinically important. Values outside the dashed line are clinically important, but how do we then reconcile that with the confidence interval? So let's start with the first one, A, study A. Who would like to interpret that for us? How do you interpret study A? You got
Uh,
10 kilos weight loss. Yeah.
yeah.
So what's your interpretation?
Um, uh, I am.
Yeah, go ahead. We can't hear you.
Can you hear me?
Yeah, now we can hear you.
Yes.
Yeah, it is outside the 95%.
So
So
it's
this value does not represent my population parameter.
well, it's outside your clinically indifference range, which is minus plus or minus 5 kilos. So this is clinically, your point estimate is clinically important because it's 10 kilos. The interval is 8 to 12 kilos, right? So the interval doesn't cross clinical indifference. Therefore, you can say this is a clinically and statistically significant result, right? Now we go to B. If you look at B, the point estimate is within clinical indifference, plus or minus 5 kilos. So this is not clinically important result. But look at the interval. This interval doesn't cross the null value, which is 0. So this interval is statistically significant, but clinically useless. So in other words, your result is a statistically significant result. 2.5 kilos weight loss is very, very statistically significant, but it's clinically useless. Why is it clinically useless? Because it's within the range of indifference, the point estimate. So the diamond is the point estimate, and the bars and the vertical line is your interval. So this interval, because it's so narrow, the sample size must be huge in this study, right? So it gives you a narrow interval which doesn't cross the null. Therefore, this is statistically significant according to significance testing, and clinically useless because the value is too small to be of use clinically. Look at C. You got a very large weight loss, but it's a very small study, so the interval crosses into your clinical indifference range, so you are not certain. Okay, it is a clinically important effect. Your p-value is also going to be below 0.05. This is a statistical significant result as well, because your interval doesn't touch the null value, right? So your p-value is definitely less than 0.05. But this is a, as I said, this confidence interval is an interval of test hypothesis. And this point estimate is compatible with a test hypothesis, which means a population parameter within clinical indifference, and therefore you're uncertain whether this is a useful result or not. So even though this is statistically significant, you don't know if it is useful or not. So now on the left side of this big dash line here are three studies. All three are statistically significant. Yet the first one is considered useful, the second one is considered useless, and the third one is I don't know. So you can see statistically significant results do not tell you whether you have an important result, which is a useless result, which is B, or I don't know result, which is C. No idea. You need both the p-value and the interval and the point estimate to make that decision, in addition to having your clinical uncertainty. Now, these three studies, D, E, and F, all three are not statistically significant. But if you look at D, it's not statistically significant because the difference in weight loss is exactly zero. And once you have a difference that's exactly on your null hypothesis, no sample size can make it statistically significant. So this is not statistically significant and a useless result because there's no difference in weight loss. On the other hand, these two have big effects, right? But the uncertainty is great, which means that even in a null hypothesis of zero could have generated this study result and this study result. And so again, these two results, even though not statistically significant, are I don't know results and needs to be verified in future studies, which means you need to do more studies, conduct a meta-analysis, and then decide, because meta-analysis will then give you more power. This is how we use p-values and confidence intervals to decide about results of clinical studies. So I have given a few suggestions in the slides for how to interpret in the previous language and in a new language these 6 studies. So I'm not going to talk much about these. I'm just going to leave it here so it gets recorded, and you can revisit the recording and look at this. And then this is the first 3 studies that were statistically significant, and these are the next 3 studies that were not statistically significant. And you can see how we differ in the language in which we speak about these results. And this will then give you an idea as to how we should be interpreting p-values, confidence intervals, hypothesis tests, and significance tests in the medical literature. So this is my summary. The main issue is epidemiology has the responsibility for having used ordinary words to have technical meanings. Like significance and confidence are ordinary words. And the people who created them did not think that these ordinary words will mislead the whole population of doctors. And that's exactly what has happened. Confidence and significance are completely misleading. And that's what has caused the whole misinterpretation that we are seeing today. Now, the interpretation clinicians usually give is the English language interpretations of these words. So when you say statistically significant, a clinician immediately thinks, oh, this is a great result. It's significant, means something great. That's not at all what Ronald Fisher meant. What he meant was, given your hypothesis, your result is unusual. So he meant unusual, but he called it significant, which is a real problem. And confidence interval, they meant uncertainty in the test hypothesis that could have generated your study data, and this, instead of calling it uncertainty, they said confidence. To me, it's like promoting deceptive statistics sales practices. You know, like the drug reps who come to sell you a drug in the hospital. They say, "Oh, if you prescribe this for your patient, I'll send you on a holiday to Switzerland or something." That's basically what's happening with statistics. So you have to be very careful about this. I am advocating harm reduction by using words whose ordinary meanings are less distant from the technical concept. So that's why my suggestion is, when you hear confidence and significance, in your mind, think uncertainty and divergence. Then you will never be misled. So instead of somebody tells you the confidence interval is so and so, in your mind, think the uncertainty in the test statistic is so and so. And if somebody says there's a statistically significant result, in your mind, just think this is a statistically divergent result, right? So it's an uncertainty interval and statistically divergent result. Then you will never make a mistake ever about interpreting this. This is what I suggest you should write in your papers. But again, it's up to you. I mean, it gives you a clear idea of what the whole thing is about, but you can rewrite this in your own language to suit your purpose. But it gives you the general direction in which we want to move. So this is basically what I always end with, saying, if you focus on this paragraph, rewrite it in your own words, plop it in your papers, you will never be misled or mislead other people. So thank you very much. I think we have come to the end of this whole discussion. And if you have any questions, now is the time to ask.
Thank you very much, Prof. Suhail, for such a very comprehensive and detailed explanation. I think it's a pretty heavy scientific dose, but it's well, like very well explanation for such an important concept of p-value and the confidence, or let's say uncertainty interval. And to be honest, I personally benefited from the difference between the hypothesis testing and the significance testing. So to me, the things were not that clear as you've kindly explained them. So if anyone has any question, please go ahead.
Thank you very much, Professor.
Yeah.
Please, can you return back to the last curve? I have a question regarding it.
This one or this one
Yeah,
or
yeah. No.
this one?
No.
This
The
one?
previous one. No.
I think he means the one with the six
Yeah.
studies.
With six studies, yes.
Okay.
Yes, this. Regarding those six studies,
Yeah.
okay. If I put them in a normal distribution curve, okay.
Yep.
Let assume that those six studies are in a normal distribution curve. If I have a question of those six studies, what exactly represent the population parameter,
So,
regardless the statistical results,
okay.
according
So,
to you?
yeah. So, first of all, you can't put these six studies in a probability distribution, sampling probability distribution, because the sampling probability distribution is dependent on sample size. All of these six studies have different sample sizes. So, they will have their own shape and height of the sampling distribution, but the center will always be zero, because we are saying the null hypothesis here is zero for all of them, right? So we'll have the same center. The mean will always be zero for the six probability distributions, but they'll all be different size and shapes based on your sample size, correct? Now, each of these point estimates, which is the diamond, you can plot them on the sampling distribution. Wherever the fall, that's your p-value, right? The extreme areas under wherever the fall, that's your p-value. And that p-value would be statistically significant for these three and not statistically significant for these three. And we know that because we calculated the intervals for each of them. So the intervals are just the converse of significance test, right? So that's how Neyman and Pearson came up with the interval. It's just the opposite of the significance testing. So these intervals have nothing to do with hypothesis test. That's a separate issue. So intervals and significance tests are converse of each other. Hypothesis tests are a bit different. Does that make sense?
Yes, yes. Thank you, Professor.
All right. Any other questions?
I think that nailed it. Rania and Maab, do you have any questions?
No, I do not.
Okay. All right, then. It was a pleasure to give this lecture to all of you, and I do hope you have benefited from it. Thank you very much for inviting me, and we hope to see you again in the future.
Yeah, thank you very much, Professor. It was a real pleasure having you with us, and جزاك الله كل خير. السلام
Okay.
عليكم.
Wa alaikum assalam.